Right, can everyone hear me okay? Okay, so my name's Gavin, I'm in Math Finance. I'm gonna leave right at 8, so if you have any questions, you can contact me here if I get back to everyone. So I'm gonna talk about the Quasi-Monte methods, which are really trendy right now in Math Finance. And what we use them for is Math Finance, there are a lot of calculations over intervals, functions, and many variables, where this S is really, really large. And as we know from our calculus classes, integration is really hard. So a much easier way to approach this is we pick a bunch of points inside the cube that we're integrating over, so that 0, 1 to S, and then we find an average of them. And there are a couple of different ways to do that. So with Monte Carlo, what you do is you choose an IID set of points inside 0, 1 to the S, and you calculate the function value there, and you take the average of them, and that's your heuristic for this value in the interval. QMC is a variation of this, where the change is that you have a deterministic set of points, and then you scramble them. And the scrambling induces randomness, but in a way such that they still preserve these uniformity properties, which can help make the estimates more accurate, or reduce the variance in certain cases. So this is really trendy because we found that in certain cases it has an advantage as a heuristic over Monte Carlo. And for researchers, I was doing this project as a research assistant, and they wanted to determine cases for certain functions where QMC outperforms MC. So for previous work on this, take this up. So my supervisors found that if F is a function of 2 variables, so x1, x2, and it's monotone each coordinate, so it's either increasing or decreasing with respect to changes in x1, x2, then QMC is always going to outperform MC. So that was a paper by Gavin Orok. I don't remember the exact name, but if you want the paper, just email me, I'll send it. And the idea for the project is we want to extend this to higher dimensions, and we want to see if this still holds. And the answer is no. I'll see how I come. Okay, so okay, so before we get into why this isn't true, we need to cover a little bit of technical background. There's no getting around it, but I'm going to try to minimize the technical details. Okay, so that set of points I was talking about earlier, we choose a set of points strategically to get an estimate using QMC. The particular sets of points we choose are called digital nets. And we choose them with respect to a certain prime base B And it's a set of points inside the Q01 sequence such that, so for the set of dimensions 1 to S, all right, I need a set of parameters T and S, where this is the dimension. This is a quality parameter, where we, the lower T is the higher quality our net is, and we'll show why a bit later. And this N indicates the number of points in our net. The number of points is B raised to the N. This is just chosen so that the math works out really nicely. So what we do is we select a set of non-negative integers, Q1 to QS, and for a TMS net, whenever this is less than or equal to M minus T, we're going to divide up the dimensions of our box according to the parameters Q1 to QS here. So say if Q1 was equal to, I'll do a really simple example in 2 dimensions. So say I choose a prime base of 2 dimensions. Okay, so N, I'm going to choose M equal to 2. So we're going to have 4 points in our net. And this is 0, 1 squared here. So I'm going to divide up the dimensions according to the parameters Q1 to Q2. So let's say that Q1 is equal to 1 and Q2 is equal to 0. So I'm going to make a grid division of this box here. Q1 is equal to 1, so each of these, I'm going to divide it into pieces of b to the minus 1, or so each of these has length a half. And Q2 is 0, so each piece is going to be b to the 0 or 1, so I'm not going to touch this. And I want there to be exactly b to the m minus the sum of these parameters inside each of these boxes. And I repeat this for all combinations that equal any k less than or equal to m minus t. It needs to work for all of them. And if this is satisfied for each k, then this is at least a m minus t net. And we assume that this t is as small as possible. So if we say it's a TMS net, then it's not t minus 1 ms net. Okay, so is that sort of clear? Or? Okay. Yeah.
Right. So what do Q1 and Q2 represent again?
These are just the ways that we're going to split the dimensions of the boxes.
Okay, got it.
So if this was 2, I'm going to divide each of these blocks into b to the minus 2, or so they have length b to the minus 2. If it's 0, I'm not going to touch it. If it's 5, I'm going to divide it up equally so they're all b to the minus 5 on this dimension. And I repeat this for each of the dimensions. So I might have a division here. That's equal to 2 into 4 pieces. Okay. Right. So that's the most technical it's going to get. You also need to know what an antichain is. So an antichain is a set of vectors of the same length. So so it's a set of vectors of the same length such that no vector is less than or equal to another one inside the set. So like 0, 1 is 0, 1, 1, 0, is an anti-chain, but 1, 1, 1, 0 is not, because this one is less or equal to that one. Okay. Straightforward. So the approach that we tried at first, because we thought that we could extend the pattern to higher dimensions. So what we were trying to do is look at these unions of anchored boxes. This L here is an anti-chain. So it indexes which vectors inside it for ik, for a given vector k, k1 to ks. This is just a box with dimensions e to the negative k1 in the first dimension, e to the negative k2 in the second dimension, e to the negative k3 in the third dimension. I'm not going to draw the fourth dimension. And you can get the idea. Okay. So, yeah, see, if we didn't have an anti-chain, then we could have boxes that are, you know, inside other boxes. So this just removes redundancy. And the approach that we were trying to use is, so in order to prove that Quasi-Monte Carlo outperforms Monte Carlo, we wanted to have a smaller variance. So what is the variance of the Quasi-Monte Carlo method? Well, it's equal to this, where this is the covariance of any 2 points chosen from the scrambled net. This n is the number of points inside the net. This sigma squared, that's the Monte Carlo variance. So, if we know this is negative, we know it's going to perform better. If you want to show this for higher dimensions, this is always going to be negative, or find a counterexample. But we thought this is always going to be negative, so this is what we tried at first. So show that we can't find an exception. To do that, we look at these functions. So this, right, I need to explain the covariance function first. So the covariance of any 2 points with respect to a certain function f, this is equal to integral of the joint PDF of the Quasi-Monte Carlo simulations. I don't think I have enough time to cover it, but it's basically a step function, and it's so it's a simple function. I said step, I meant a simple function, and it's constant on these sets dis. It's not really that important what those are. But so you evaluate this interval, and you subtract this one. This gives you the covariance, and in order for this to be negative, we want this to be smaller than this in all cases. And this is when so this is where my computer comes in, because it's a lot easier for my computer to try thousands of these cases than it is for me to. So I write a program that computes these. This is the joint PDF of the with respect to the function f, and in particular, we're focusing on these functions, the indicator function of the union of anchor glosses, because this decomposes into a form that's fairly easy for my computer to compute. So I try a whole bunch of cases. Right, so with respect to the indicator function, this joint PDF expression, so when you sub this in, it's just going to be the union over the Cartesian product of that set with itself. Same here, although this will have the joint PDF attached to it. So in terms of the expression that my computer can compute, looks like this. You don't really need to worry about all these symbols. If you want, I can explain them after, but there's no way I'm going to explain them right in presentation. But basically, it's a sum of terms with respect to the base of the net and the n parameter in the net. So it's something concrete that I can plug into my computer and I can calculate a whole bunch of examples. Of course, the problem here is that we're summing over a power set, so this is going to be exponential in terms of the length of the set. So when we're working in higher dimensions, it's going to get, or even with just small antichains and low dimensions, it's going to get really tricky really fast. But I got lucky. Turns out that this has, that is, oh sorry, I didn't explain that. That's the joint PDF expression. For the double volume, you just replace this with 1. So it's no longer present. It turns out that the joint PDF for this one is greater than the volume. So it's a counterexample in 5 dimensions. According to my computer, at least. And it's nice to think that you've solved the problem, but you don't really know if you've solved it unless you write up a proof, right? So how do we know that this is actually a counterexample? How do we know it wasn't a floating point addition error? So I get my computer to print out the output as it's working, and I check through all of it. Looks good, looks good, looks good. And it seems like it works, right? But that's not a form that other people can read and verify in the future, so I get my computer to write up a proof because the calculation is very long. And so it does. It writes up a full proof, very explicit steps of its calculation here. And then it plugs in the values. It shows that this is the joint PDF is greater than the volume. And it does it in only 18 pages. Oh, sorry. Okay, so we found one in 5 dimensions. how do we know that it's going to work in higher dimensions? Or the patterns stop at 5 dimensions maybe, and then it continues to always be better in 6 and up? Well, it turns out that you can generalize this case to higher dimensions by just adding on zeros. It's like my dream. I get infinitely many other counterexamples by basically adding on known new information. The projections work out so nicely. And the only thing left is that the only extra thing that you need to account for is that this prime base B needs to be greater than or equal to the dimension, according to the way that these nets were constructed. So you get your computer to, instead of actually just computing this with numerical values, you find polynomials, and then you show that the polynomial corresponding to the joint PDF is greater than or equal to the polynomial corresponding to the volume. That's fairly easy optimization for it. Just show the first part is positive, and then you take the derivative and show that's positive, so it's always going to be greater than or equal to 0. Okay. So we have 5, we have 6, we have 7, we have 2, what about 3 and 4? And I tried a similar method with my computer. I was working on this for like 2 months, trying to find counterexamples in 3 and 4 dimensions. And at the same time, I was simultaneously working on something completely different, which was related to looking at the functions for which Quasi-Monte Carlo performs poorly in terms of having an unbounded Vitali variation, but having a well-behaved variance. And so my computer search turned up nothing, and by pure serendipity, the other method that I was trying ended up finding a counterexample in 3 dimensions. And it turns out it works if you look at this function f, which is also monotone each coordinate. Right? This is increasing each. This is strictly decreasing each coordinate because it's 1 up until this gets big enough, and then 0. This is increasing in the x3 direction. It turns out this is a counterexample, but there's a loose end to this project, which is why I wanted to talk to the class about it, and that's this dimension. And we don't know if the patterns will continue for s equals 4 or not. And my guess is that most likely it doesn't continue. And if I were to spend more time on this project, the function that I would try is this one. x3, x4. I have a hunch that this will also lead to a positive covariance, which means that Quasi-Monte Carlo has a higher variance than Monte Carlo, so it doesn't perform better than it. But as of this point, this is unsolved. And then in the future, we want to eventually look at continuous functions, because right now we're looking at these kind of contrived cases of monotone functions, which don't really reflect common functions used in finance. So it might be some way to extend these indicator functions to other types of continuous functions and apply this research to real world problems. But until then, we're just going to continue inching away with progress on trying to understand this. So I think this really reflects a lot on the serendipity of mathematics, right? I was playing around with my computer and ended up stumbling across something that violated our initial assumptions. I ended up finding something completely out of the blue. I was working on something completely unrelated to the current problem that end up connecting directly to something else. There's a point of beauty in randomness. Maybe.
Why would we expect quasi-Monte Carlo simulations to be better in the first place? Like, it's like you would expect like the reason that Monte Carlo works is random and like there's no real pattern, so there's no kind of bad input. And if you add some kind of structures that creates something that potentially could be exploited. You get what I'm saying? Like, there's no reason in my mind why you would expect Quasi-Monte Carlo to be better than Monte Carlo. Is there a reason why you initially expected the opposite?
Well, it's not that it's completely deterministic. There's randomness induced from the scrambling of the points. Yeah, there's some properties preserved in terms of the structure of the net. So that's why there's still some cases where it doesn't perform better than Monte Carlo. Like, it's not going to always perform it, but we find that it does in many relevant cases. Because there's still an element of randomness, even though it's a little bit more structured in terms of how it's generated. Your question? Okay. If you have anything else, that's my email.